Good afternoon. So we are back for the fourth in the 11.2 series videos. And to get us started, what's that? Eva?
Knock, knock.
Is this another joke?
Yeah.
Okay, well, let's try again. Go ahead.
Knock, knock.
Who's there?
Pandemic.
Pandemic who? Oh, that's right. I guess no one. It's a pandemic out there. I don't know if it's too early for that joke or not, but we will see. We'll be here all day. Actually, we'll be here for quite a while, apparently. But anyhow, on to the mathematics. That's what we're here for. Today we're going to continue on our discussion of series, and if we were proceeding as we would in class, this would be the beginning of day 2, so I would of course start off with a fantastic recap of what we'd previously encountered. So let me go ahead and remind you what we've been talking about. We've been talking about these things called series, and a series, and for us it's always an infinite series, is what we get when we add up the terms in a sequence, where a sequence is just a list of numbers in a specific order. So this would be A1 plus A2 plus dot 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 plus A sub n, and it just continues on indefinitely. And the question we want to answer is, does the series converge or diverge? And we've defined, I guess, more formally convergence and divergence in terms of the limit of the sequence of partial sums, which, when it is necessary, it's a really useful thing. So if we let S sub n be A1 plus A2 plus all the way up to AN, i.e. adding up the first n terms, and this sequence of partial sums converges to a number S, then that number S will in fact be the sum of the series. That is, the sum from n equals 1 to infinity of A sub n is the limit as n approaches infinity of S sub n, so kind of like an improper integral we mentioned before, which is S. The other big thing we hit on was the idea of a geometric series. A geometric series is something of this form: the sum from n equals 1 to infinity of AR to the n minus 1, and this will equal A over 1 minus R if the absolute value of R is less than 1. And it diverges when the absolute value of R is bigger than or equal to 1. And note that in terms of identifying these quantities, we think of A as being the first term in the geometric series, and R as being the common ratio. So let's begin our discussion today by looking at an example of one of these geometric series. So the question we have is, does the series given here converge or diverge? And the key thing that we need to do to get started is really just a bit of algebra, exponential algebra, that is. So if we rewrite this, we would say this is equal to the sum from n equals 1 to infinity, 2 raised to the 2n power would really be 2 squared to the nth, using properties of exponentials. And because of this minus sign here, I'm going to take the 3 to the 1 minus n and put it in the denominator. And if we put it in the denominator, we need to take the opposite, or a negative, of that exponent. So 3 to the n minus 1. And then I'm going to take this a step further in terms of algebra, and then we'll see what that leaves us with. So 2 squared is 4, and 3 to the n minus 1 I'm going to leave exactly as is, because now I'm just going to write this out. We have when n is equal to 1, so a 4 over 3 to the 0, plus when n is 2, 4 squared over 3, then when n is 3, 4 cubed over 3 squared, then 4 to the 4th over 3 cubed, and it just keeps going indefinitely. Note, to get from one term to the next, at each step we're multiplying by 4/3. And our first term is 4. So this is a geometric series with a equals 4 and r equal to 4/3. And take a moment, pause the video, and write down on your paper or tablet or device of choice that you're using here, does this series converge or diverge? And because you've taken a moment here now, I don't know, because the absolute value of r is 4/3, which is bigger than or equal to 1, this is a divergent geometric series. And I know the question's always kind of, what do we have to show? Well, somehow you have to indicate what is r, tell me its absolute value is bigger than or equal to 1, and make that conclusion that it diverges. Another thing to note is our indication that we had a geometric sum was when you have numbers like 2 and 3 raised to these quantities involving n. Now for future reference, we're going to investigate something called the harmonic series. So the harmonic series is the sum from n equals 1 to infinity of 1 over n. And the fact that it's given a name, sorry, my daughters are reading books in there for their, recording them for their librarian. But anyhow, it's called the harmonic series. It has a name. That's because it is something that's important that comes up in future applications. So this would be 1 plus 1/2 plus 1/3 plus 1/4 and so on. And it turns out that this series diverges. And we're going to have another way of showing that it diverges in our next section, 11.3. But for now, there's kind of a really neat way to go about this that I think is worth kind of just giving you some intuition with. But it's not something I would ask you to recreate or kind of recall in the future. So that's not an indication that you should stop and fast forward the video either. Okay. So if we write out these terms, we have 1 plus 1/2, and I'm just kind of organizing them slightly differently here, plus 1/3 plus 1/4, and we'll see where we're going with this. And then I'm going to group together 4 terms, so it's 1 term plus 1 more term plus 2 terms and 4, then we're going to go 8, and then we're going to go, gosh, hopefully not, but 16, and so on. So let's see here, then we would have 1/5 plus 1/6 plus 1/7 plus 1/8. Then we would have, continuing on, plus now 8 terms together. 1/9 plus 1/10. Don't worry, we're not going to write all these down. All the way up to 1/16. And we can keep doing this indefinitely because there's always going to be another group of terms with twice as many as a step before it because this goes on indefinitely. And I'm going to make just a simple observation here. In terms of how we've grouped these, note that 1/3 plus 1/4, that is larger than 1/4 plus 1/4, which is 1/2. And the reason I say it's larger is because remember, dividing by something bigger, the 1/4 versus 1/3 here, gives you something smaller. Similarly, note in this group of 4, 1 over 8 is the smallest of those 4 terms. So if I wanted something smaller than all 4 of those, I could say it's 1/8 plus 1/8 plus 1/8 plus 1/8. And what do you get when you add up 1/8 4 times? Yeah, you nailed it, 1/2. Similarly, we have this next group of 8 terms. Each of them is bigger than 1/16. And 1/16 added up 8 times is 1/2. And we can keep doing this indefinitely. Each of these groups we're adding up, infinitely many of them on the left, each and every one of them are larger than 1/2. And what that tells us is if we take the series in its entirety, the sum from n equals 1 to infinity of 1 over n, something smaller than it would be, well, 1 plus 1/2, the first 2 terms, and that's actually equal to it, but the smaller than it part would be the 1/2s that come afterwards. So those next 2 terms are bigger than 1/2, and then the next 4 terms are bigger than 1/2, the next 8 terms are bigger than 1/2, the next 16 terms are bigger than 1/2, and so on. And kind of a funny sounding question, but if we take 1/2 here and we add it up infinitely many times, there is no possibility that could converge and give you back something finite. So this stuff that we're adding up, I'm going to say goes to infinity. I really want to say equals infinity, but remember infinity is not a number. So the best I can do is say that if you add up 1/2 a whole bunch of times, it just gets arbitrarily large. And if this series we are interested in is larger than something that blows up to infinity, thinking of our comparison test with improper integrals, what we're going to do is make our conclusion. The harmonic series diverges. And that completes part 4 in our videos from 11.2 on series. We'll have 2 more parts here. One more going over a few more kind of common properties in a very useful test. And then part 6 will go over a worksheet that you all will have to work on. So take care.